Okay, so for L equals 0, ML equals 0, the probability is independent of theta. Okay? Probability density is independent of theta. For L equals 1, ML equals 0, what we find is that we have, if we look along the z-axis, the probability that's where we have the biggest probability of finding the electron. Okay, and we have 0 probability of finding it if we look in some direction perpendicular to the z-axis. Okay, now just let me pause really quick and say that if you notice all the ML equals 0 states, that is this one, this one, this one, and this one, have a large probability density along the z-axis. And this, in some sense, makes sense, knowing that when ML equals 0, that means that we have no, we've seen that ML quantizes the angular momentum in the z-axis. Well, if we're going to have any angular momentum in the z-axis, along the z-axis, that means that we can't find the electron. That means that, remember, to have angular momentum along the z-axis, that means that the electron has to basically be orbiting around the z-axis. If it's oscillating along the z-axis, that does not contribute to angular momentum along the z component of the angular momentum, and so this makes sense. Okay. And then for L equals 1, ML equals plus or minus 1. Okay, we have, now we have the opposite. So if we look along the z-axis, we have 0 probability of finding the electron. Okay, or finding the particle. But if we look along mostly along the xy plane here, then we have a higher probability. And now again, this is satisfying. If we're going to have a z component of the angular momentum, we would expect that we would find the particle most likely in the xy plane, and that's what we see here with some uncertainty. Okay, so there's some probability that we find it above or below the xy plane, but we find it predominantly along the xy plane, which helps contribute to the fact that it has a z component of angular momentum. Okay, and we see that for all the ML equals the highest ML numbers, so ML equals plus or minus 2, plus or minus 3, plus or minus 1, we see that as we go up in ML, we see that this orbit flattens out even more and gets elongated even more, indicating, justifying, if you will, rationalizing that the fact that we have larger z component of the angular momentum as characterized by the larger value of m sub L. Okay, we see these sort of more interesting and complicated states as you go up in L. Okay, so here we have something which looks a little bit like the L equals 1, ML equals 0 state. Okay, it's another ML equals 0 state, but now we have this sort of disk in the center and these clover leaves. And the point is that any time that ML is not equal to 0, okay, you have 0 probability of finding the electron along the z-axis. Okay, and that is important because, again, if the z component of the angular momentum is non-zero, then you better not find the particle along the z-axis, because if it were all along the z-axis, then it would not be able to contribute to a z component of the angular momentum. Okay, so that's a representation, kind of a 2D representation of the polar functions. Now, if we look at the spherical harmonics in some sort of quasi 3D view, then we get this. Here's the L equals 0, so L equals 0, ML equals 0 state. All the ones down the center here are the ML equals 0 states. We go from ML equals minus 3 to ML equals plus 3, L equals 0 to L equals 3. And when you see this sort of green, that's meant to indicate that the wave function is, so this is not the wave function square now, this is just the YLMs, or it's a representation of that. So this corresponds to negative values of the wave function, this corresponds to positive values of the wave function. If we squared this to get the probability density, obviously these would both be positive.